40 light-years from Earth, a tiny red star is surrounded by 7 rocky worlds, all roughly the size of our planet. When astronomers found this system in 2017, it became the most celebrated planetary discovery outside our own. 7 Earth-sized planets, 3 inside the habitable zone. A star close enough for James Webb to study their atmospheres. For the first time, we had a realistic chance of detecting signs of life on another world within our lifetimes. That was the promise. But Webb has now spent years observing this system, and what it is finding is not what we hoped. The atmospheres are not showing up. The star is far more hostile than the optimism allowed, and the planets that seemed like candidates for life are being crossed off. The system is called TRAPPIST-1, named after the telescope that first detected it, the Transiting Planets and Planetesimals Small Telescope in Chile. The star at the center is an ultra-cool red dwarf, classified as spectral type M8. It has less than 10% the mass of our Sun and is only slightly larger than Jupiter. It is so dim that you could never see it with the naked eye, even though it sits in the constellation Aquarius, cosmically speaking right next door. If you replaced our Sun with TRAPPIST-1, Earth would freeze in total darkness within days. That is how faint this star is. What made the discovery remarkable was not just the star. It was what orbited it. 7 planets, all of them rocky, all of them roughly Earth-sized, packed into orbits so tight that the entire system would fit inside the orbit of Mercury. Their years last between 1.5 and roughly 19 Earth days. They are so close together that if you stood on the surface of one, the neighboring planets would sometimes appear larger in the sky than our moon does from Earth. And critically, 3 of them, planets E, F, and G, receive levels of starlight that could theoretically allow liquid water to exist on their surfaces. That combination was almost too good. 7 terrestrial worlds around a small, nearby star. A system compact enough for Webb to observe, with the precision needed to detect atmospheric molecules during transits. No other known system offered this many promising targets in one place. It was unprecedented. Scientists described it as a natural laboratory for understanding rocky planet atmospheres. The excitement was justified. But it was also fragile, because it rested on an assumption that turned out to be far more uncertain than anyone acknowledged at the time. The assumption was that Earth-sized means something close to Earth-like. It does not. And that is the lesson Webb is now delivering, planet by planet, spectrum by spectrum. Start with the innermost world. TRAPPIST-1b. In 2023, a team led by Greene used Webb's mid-infrared instrument to measure the planet's dayside temperature during a secondary eclipse. The brightness temperature they recorded was consistent with a dark, bare rock, absorbing and re-radiating starlight with almost no heat redistribution to the night side, no thick carbon dioxide atmosphere, no significant envelope of any kind. The data pointed strongly toward an airless surface, scorched and fully exposed to space. Then came a deeper look. In late 2024, a combined analysis of eclipse observations at 2 different infrared wavelengths introduced some nuance. The results were not perfectly consistent with the simplest bare rock model. A dark surface without weathering could suggest ongoing geological activity, or alternatively, a thin, hazy carbon dioxide atmosphere might also fit. But in 2026, thermal phase curve observations published in Nature Astronomy largely closed that door. The phase curves showed that TRAPPIST-1b emits thermal radiation in a pattern consistent with a rocky surface that lacks any substantial atmosphere. The night side is cold, the day side is hot. Heat is not being moved around by wind or convection or any circulatory process. The planet is almost certainly exposed. TRAPPIST-1c told a similar story. Secondary eclipse measurements in 2023 disfavored a thick carbon dioxide atmosphere. The same phase curve study confirmed the pattern. TRAPPIST-1c may retain a tenuous oxygen-dominated envelope with very little greenhouse effect, or it may be just as bare as its neighbor. Either way, the data rule out anything resembling the kind of atmosphere that could support liquid water or protect a surface from radiation. 2 planets down, neither one habitable in any meaningful sense. Neither one carrying an atmosphere that could shield a surface or cycle water. Then, in August of 2025, the results for TRAPPIST-1d arrived. This planet sits right at the inner edge of the habitable zone. It receives only about 4% more starlight than Earth. Of the inner 3 worlds, it was the one with the strongest theoretical case for retaining an atmosphere. Caroline Piaule-Gorayeb of the University of Chicago led the study, using Webb's near-infrared spectrograph to observe 2 consecutive transits. The instrument searched for molecular absorption features, the chemical fingerprints of water, methane, and carbon dioxide that would indicate an Earth-like atmosphere. It found none. The transmission spectrum was flat. Piaule-Gorayeb was careful to note that this did not absolutely prove the absence of an atmosphere. The planet might have an extremely thin envelope, difficult to detect, somewhat like Mars, or it might be shrouded in thick, high-altitude clouds that block molecular signatures, more like Venus. But the simplest interpretation, the one the data most comfortably support, is that TRAPPIST-1d has no atmosphere at all. As Piaule-Gorayeb put it, the planet can be ruled out from the list of potential Earth twins or cousins. 3 planets examined, 3 atmospheres absent or vanishingly thin. And behind all of these results sits a deeper problem that is not about any single planet. It is about the star. TRAPPIST-1 is volatile. Research published in 2025 using Webb data found that the star flares roughly 6 times per day. Each year, it produces between 4 and 6 superflares, events that release enormous bursts of ultraviolet and high-energy radiation into the faces of its closely orbiting planets. Ward Howard, the NASA Sagan Fellow who led the flare study, noted that when astronomers first began observing TRAPPIST-1 with Webb, they had not anticipated how many transit observations would be contaminated by flare activity. The star's surface is covered in active regions, star spots and faculae, that distort the light passing through any planetary atmosphere during transit. This is called stellar contamination, and it has become one of the single largest obstacles to studying this system. The contamination matters because it does not just make the data noisy, it introduces false signals that can mimic or mask atmospheric features. When starlight passes through a planet's atmosphere during transit, specific wavelengths are absorbed by molecules in the air. But if the star's own surface has patches of different temperature, those patches imprint their own spectral features onto the same signal. Separating what belongs to the planet from what belongs to the star becomes extraordinarily difficult. For the inner planets, this is largely academic since they appear to have no atmospheres, but for the most important remaining target, it is the central obstacle. That target is TRAPPIST-1e. Of all 7 planets, E sits most squarely within the conservative habitable zone. Climate models suggest it could sustain surface temperatures near 279 Kelvin under a clear atmosphere, close to Earth's average. Its mass and radius are consistent with a rocky composition. In 2025, Anna Glidden of the Massachusetts Institute of Technology published the first Webb transmission spectra of TRAPPIST-1e. The results were neither a detection nor a clean non-detection. Stellar contamination was present in every observation. The data could not strongly distinguish between a planet with a modest atmosphere and a planet without one. Venus-like and Mars-like compositions were disfavored. Hydrogen-rich atmospheres with traces of methane and carbon dioxide were excluded, but nitrogen-rich atmospheres with traces of methane and carbon dioxide remained permitted. The planet's atmospheric status is genuinely unresolved. To address the contamination problem, astronomers have designed a multi-cycle Webb program that observes closely spaced transits of both TRAPPIST-1e and TRAPPIST-1b along nearly the same path across the star's disk. Because B appears to be a bare rock, any spectral features shared between the 2 transit observations are likely coming from the star rather than from a planetary atmosphere. By subtracting those shared features, the team hopes to isolate whatever signal belongs to E alone. Early modeling suggests that with approximately 15 corrected transit observations, a carbon dioxide-rich atmosphere on TRAPPIST-1e could be detected if one exists. But that is a conditional statement, and the condition is steep. 15 corrected transits through a star that flares 6 times a day. Years of telescope time on a single planet, with no guarantee that an atmosphere is there to find. This is not the confident, sweeping discovery the original headlines promised. This is slow, painstaking, deeply uncertain work on the most important remaining candidate in a system that was supposed to offer 7. Planets F and G also sit within the habitable zone and remain uncharacterized, but they are colder and harder to observe, and their atmospheric prospects depend on the same hostile star. And that is the harsher truth. Not that TRAPPIST-1 is dead, not that Webb has ruined anything. The telescope is doing exactly what it was built to do. It is replacing hope with evidence, and the evidence is narrowing. The system that once symbolized our best nearby chance of finding life beyond Earth is turning out to be a far more selective, far more punishing environment than the early excitement allowed. The inner planets are likely bare rock, stripped or never clothed by atmospheres under the relentless radiation of a hyperactive star. The planet closest to the habitable zone that Webb has managed to characterize, TRAPPIST-1d, shows no sign of the molecular signatures we associate with a living world. And the prime habitable zone candidate, TRAPPIST-1e, is so difficult to observe that even the most powerful space telescope ever built cannot yet give us a clear answer. What TRAPPIST-1 is teaching us may ultimately be more important than whether any single planet hosts life. It is teaching us that proximity does not equal hospitality. That 7 Earth-sized worlds can orbit a single star and still offer almost nothing resembling the conditions we take for granted here. That the habitable zone is a geometric concept, not a guarantee, and that the distance between the right size and the right conditions is vast. The system is not a failure. It is a recalibration of expectations. It is showing us, in precise and sometimes uncomfortable detail, how quickly optimism narrows when better instruments arrive and when assumptions meet measurement. The easy version of TRAPPIST-1, 7 nearby Earths waiting to be explored, belonged to the era before Webb. The real version is harder and far less forgiving, and the most unsettling part may be this. If one of the most promising nearby systems we have ever found is turning out to be this difficult, then the universe may be telling us something about how rare the conditions for life truly are. Not impossible, not ruled out, but far more demanding and more selective than our first hopeful glance suggested. Somewhere in the data still being collected, TRAPPIST-1e may yet hold a surprise, but whatever that answer turns out to be, the system has already changed the conversation. We no longer ask whether nearby Earth-sized planets exist. We already know they do. We ask whether any of them can survive the stars they orbit. And that is a much harder question, one that will take decades of careful observation to answer. Thanks for watching, and if you found this one interesting, a like or subscribe genuinely helps the channel. I'll see you in the next one.